Come on, my dears, let us proceed further in chapter number 5. Please kindly read this statement of first MCQ in the exercise. Have you read it? Look, we are given one alpha particle which is projected towards a nucleus, correct? What is an alpha particle? It is the helium nucleus. It has charge of 2 protons, okay, fine. In short, it has a positive charge and which is projected towards a nucleus. Nucleus is always having a positive charge only. So now this positively charged nucleus will repel the approaching alpha particle. So now if alpha particle has to go closer to the nucleus, it has to do work against this repulsive force. In doing that work, its kinetic energy will decrease, and at some minimum distance between nucleus and alpha particle, that kinetic energy becomes 0 for a moment. At that time, the distance between nucleus and alpha particle is found to be minimum. It is only known as distance of closest approach, shown by symbol R0, which we require to find out in this question. Got it? Let us find out. Tell me, in this process, what has happened? The kinetic energy of alpha particle has been decreased to 0, and at the cost of that kinetic energy, the electrostatic potential energy of a system made up of nucleus and alpha particle has been increased. So let us write according to law of conservation of mechanical energy that decrease in kinetic energy should be equal to increase in electrostatic potential energy. Got it? What is decrease in kinetic energy? It is half mv square. What is increase in electrostatic potential energy? By formula it is K Q1 Q2 upon R. K Q1 Q2 upon R. Instead of R, I am writing R0, which is distance of closest approach. Now just make subject of the equation R0. Transfer this R0 here. Transfer this part in the denominator. Got it? So it is now K Q1 Q2 upon half mv square. K as it is. What is the first charge? Let it be charge of alpha particle. As I told you, it is charge of 2 protons. So it is 2 into E. What is Q2 now? Positive charge of the nucleus, which is charge of Z number of protons, where Z is atomic number of given element. For 1 proton charge is E, for Z protons it would be Z into E. This half mv square as it is in the denominator. Got it? Come on. Now this is 2K. I have written here Z E into E, that is E square, denominator as it is. Fine. Now just dictate me all the values. Come on, 2 as it is. What about small k? Remembered? Proportionality constant coming in Coulomb's law, that small k was 9 into 10 raised to 9 Newton into meter square upon Coulomb square. So small k value is 9 into 10 raised to 9. What about Z atomic number? It is 50 given to you in the statement. What about magnitude of charge of 1 electron? It is 1.6 into 10 raised to minus 19 Coulomb, and then it's a square. Divided by, what is this altogether? This whole term indicates kinetic energy of alpha particle. Actually, it is decrease in kinetic energy of alpha particle, but it is equal to initial kinetic energy of alpha particle, which is given to you 10 million electron volt. Come on, 10 million electron volt you should convert into electron volt. For that you need to multiply by 10 raised to 6. 1 million or 1 mega means 10 raised to 6. But still that value of energy is in electron volt. You must convert it into joule. 1 electron volt is 1.6 into 10 raised to minus 19 joule. So you must multiply by this factor 1.6 into 10 raised to minus 19. Got it? Come on, when all the values are placed in SI units, naturally this distance will be obtained in meter, and the value is 1.44 into 10 raised to minus 14, this many meter. Got it? Kindly read this statement of number 2. Here, let us derive first of all one general result. It will be very useful to you in some other questions also. So let me derive that result, and then after I will make use of it. Okay? What is that result? I am showing you. For an electron which is orbiting around nucleus in a circle of radius r with a constant speed, that is for uniform circular motion, you know Coulombian force is just equal to centripetal force. So centripetal force is provided in the form of Coulombian attractive force. What is centripetal force? It is mv square upon r by formula. What is Coulombian attractive force? According to Coulomb's law, K Q1 Q2 upon r square. K is 1 upon 4 pi epsilon 0. Q1 is Z into E, into Q2 is magnitude of charge of electron, so it is E, ZE into E, that is ZE square upon R square, correct? 1 R is getting cancelled. What is kinetic energy? It is half mv square. So if I have mv square, I should multiply by 1 by 2. When you multiply here, here also you have to multiply. So when you multiply 1 by 2, it will become Z square upon 8 pi epsilon 0 r. Z square upon 8 pi epsilon 0 r. Okay. What about electrostatic potential energy? K Q1 Q2 upon r. Instead of K, 1 upon 4 pi epsilon 0. Q1 if you take as positive charge of nucleus, it is Z into E, into Q2 is now charge of electron, which you must write minus E. In the formula potential energy, remember, you must retain the polarity of the charge as it is. Electron has negative charge, so you must write minus E, correct? Divided by distance between center of nucleus and electron, which is r. Now tell me, minus Z E into E is square upon 4 pi epsilon 0 r. Okay. Let me multiply by 2 in the numerator and in the denominator. When you multiply by 2 here, it is minus 2z is square, minus 2z is square. When you multiply by 2 here, 2 4s are 8 pi epsilon 0 r. Correct? You must have come to know why I did like that, because in place of z square upon 8 pi epsilon 0 r, in place of z square upon 8 pi epsilon 0 r, we can write kinetic energy, that is capital K, correct? So this part is nothing but kinetic energy capital K, so it is minus 2 into K, minus 2 into K, correct? Fine. What is mechanical energy? It is summation of kinetic and potential energy, K as it is. What about value of U? It is right now minus 2K. So U equals to minus 2K. K minus 2K, it is how much? Minus K. And just find out minus K from here. Minus K, if you want, you should transfer this 2 in the denominator. So it is U by 2. So minus K is U by 2. Got it? E equals to minus K equals to U by 2. Please remember this general formula. This is applicable for any electron orbiting around nucleus in any orbit. Okay, fine. So please remember this result, E equals to minus K is equal to U by 2. Fine. Now what is the electrostatic potential energy given to you right now? it is minus E square upon 4 pi epsilon 0 r. If they have written here 8, it is by mistake. The correct value is this, minus E square upon 4 pi epsilon 0 r. Fine. What is kinetic energy from here? Transfer this minus sign over here. So K will be minus 1 by 2 into U. K equals to minus 1 by 2 into U. Now minus 1 by 2 as it is. What about U? U is minus E square upon 4 pi epsilon 0 r. Minus E square upon 4 pi epsilon 0 r. Now tell me, minus minus plus E square, 2 4s are 8 pi epsilon 0 r. Correct? So this is the final formula of kinetic energy. This is your final answer. So kinetic energy in this case is E square upon 8 pi epsilon 0 r. Got it? Kindly read the statement of number 3. Have you read it? Look. According to Bohr's atomic model, in the first postulate you have studied, orbital angular momentum of electron is nh upon 2 pi. Because h upon 2 pi is constant, L is proportional to n. When L is proportional to n, just give that relation as relation number 1. Fine. What about formula of radius of nth circular orbit of an electron? You must remember that formula. R equals to epsilon 0 n square s square upon pi m z square. Now relation between R and n square. What is that relation from here? R proportional to n square. Just speak reverse. N square proportional to R. Take square root on both the sides. When you take square root here, it is n. When you take square root here, it is proportional to under root r. N proportional to under root r. Just give the relation as relation number 2. When you combine these two relations, come on, L proportional to n, but n proportional to under root r. So if you just combine these two, then L must be proportional to under root r. When L is proportional to under root r, this is your final answer right now. But you may extend it further. Come on, mathematically if you write like this, then further you can write L1 upon L2 equals to under root of R1 upon R2. So they may give you two radii of two different circular orbits, and they may give you one angular momentum value, and second angular momentum value they may ask. Okay, so you please remember this relation. Okay, simple. Kindly read the statement of number 4. Have you read it? Tell me. We know from this formula that R is proportional to n square. R is proportional to n square. If it is direct proportionality, then 1 to 1 to. So from here R1 upon R2 will be equal to n1 square upon n2 square. What is R1? First value of radius of orbit, which is given to as capital R. Second value of radius of orbit we want to find out. What is n1? First value of order of orbit, which for first excited state you must take as 2. What is n2? Second value of order of orbit, and for second excited state that value is 3. So I am writing here 3. Now just simplify. Come on. I want R2, make it subject to the equation. 3 square is 9, 9 will go up, 2 square is 4, 4 will come down, 9 into R upon 4, 9 into R upon 4. But 9 upon 4 means, come on, 2.25 into R. Okay, my dears, don't be cheated. Don't be cheated. This capital R is not Rydberg constant. It is simply radius of first excited state. Radius of that orbit in which electron is in first excited state. Okay, fine. This R is radius and not the Rydberg constant. Okay, one thing. Secondly, please remember, what is N1? It is first value of order of orbit. If they give first state or ground state, you may take N1 equal to 1. But if they give first excited state, then you should increase it by 1. 1 plus 1, that is 2. What is N2? Second value of order of orbit. If they give second state, you may take N2 equal to 2. But if they give second excited state, then you should take N2 equal to 3. That's why I've taken here N2 equal to 3. Got it? Fine. Now, read this statement of number 5. Come on, have you read it? What is the formula of total energy of electron in nth orbit? Remembered? En equals to minus mz square e raised to 4 upon 8 epsilon 0 square n square h square. Remembered? What is the relation of this with n square? You can see in this formula, it is inverse proportionality relation. En varies as 1 upon n square. Because it is inverse proportionality, then 1 to 2 1, 1 to 2 1, En1 upon En2 will be equal to n2 square upon n1 square. 1 to 2 1. Simple. Same ratio are written here. What is n1? Come on. Order of orbit, first value of order of orbit, first value of order of orbit, but that order of orbit is given to you, come on, first excited state. Had it been first state, we could have written n1 equal to 1, but because it is first excited state, then I should write n1 equal to 2, so n1 is 2 whole square. What about n2? It is second value of order of orbit, which is given to second excited state. For second excited state, N2 will be 3. So, N2 is 3. It's a square. 3 square is 9, 2 square is 4. So, this ratio they have asked, and that ratio we have found out, it is 9:4. Simple. Read this statement of number 6. What is orbital angular momentum of electron according to Bohr's first postulate? Remembered? L equals to nh upon 2 pi. That is integer multiple of h upon 2 pi. What is n? It is order of orbit of electron, or it is also called principal quantum number. N, it is given to you n equal to 5 because they are talking about fifth orbit. So, because n is 5, what is the value of h? Planck's constant 6.625 into 10 raised to minus 34 joule into second upon 2 into pi is 3.14. Simplify, answer is 5.27 into 10 raised to minus 34. Unit of angular momentum is joule into second. Joule into second. Got it? Fine. Read the statement of number 7. One upon lambda equals to r into 1 upon m square minus 1 upon n square. Actually here it is m, but m indicates order of series. We call it series term. Values of m for different spectral series in the atomic spectrum of hydrogen you must have remembered. Come on, Lyman, Balmer, Paschen bracket fund. Respectively values of m are 1, 2, 3, 4, 5. Correct? For the last 3 series, that is Paschen bracket fund, values of m are 3, 4, 5. Correct? Then why I have not written 3 and 5 and why I have written only 4? Because you see, they want a radiation in which section of electromagnetic spectrum? In the section, come on, infrared. And for infrared radiation to be emitted, the transition must take place from any orbit to either third orbit or into fourth orbit or into fifth orbit, correct? So from any order to 3, from any order to 4 or from any order to 5. These are the possible answers. But in the given options, you will not find transition from particular order to third orbit or particular order to fifth orbit. Those transitions they have not given, but they have given one transition from 5 to 4, from 5 to 4, correct? Fine. So that is the answer right now. From n equal to 5 to n equal to 4, that transition will give you radiation having wavelength in infrared region. Got it? But in the same statement, in the textbook, they have committed one mistake in the given statement, given first sentence. You know what have they done? They have told that when electron is making transition from n equal to 3 to n equal to 2, they have said that it gives radiation having wavelength in ultraviolet region. Is very wrong. Very wrong. For ultraviolet region, which series is applicable? Lyman series. And for Lyman series, that transition must be from n equal to 3 to n equal to 1. Correct? You know what have they given? N equal to 3 to n equal to 2. Let me check it up. Just a minute. In the textbook they have given, look, they have given from n equal to 4 to n equal to 3, n equal to 4 to n equal to 3. Such a transition can never give you radiation in the ultraviolet region. No, it is very wrong. It must be from n equal to 4 to n equal to 1. If it is from n equal to 4 to n equal to 1, then it will have Lyman series, and in case of Lyman series, you may have ultraviolet radiation emitted. Got it? So, it is very wrong. But we are least concerned with that. We are concerned with the answer. Answer in this question is transition should be from n equal to 5 to n equal to 4, which will give you infrared radiation. Correct? Come on, kindly read this statement of number 8. Have you read it? Look, for Lyman series, 1 upon lambda equals to r into 1 upon 1 square minus 1 upon n square. Correct? What are the values of n? They are after 1 all the positive integers. That is 2, 3, 4, 5 dash 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 up to infinity. When you are talking about H alpha line, you should take here first value. When you are talking about H beta line, you should take second value. When you are talking about H gamma line, you should take third value. And when you are talking about H delta line, you should take fourth value. And when you are talking about this line, you should take the last value. Correct? For H alpha line, come on, value of n is 2. Value of n is 2. Just put it here. And at that time, the wavelength of H alpha radiation, I am just showing by symbol lambda alpha. Come on, this R as it is, 1 upon 1 square as it is, because value of n is right now 2, just put it here. N equals to 2. Simplify. R into 1 upon 1 is 1, minus 1 upon 2 square is 4. 1 minus 1 upon 4 is 3 by 4 into R, that is 3R by 4. Give it equation number 1. Wait. Now talk about Balmer series. For Balmer series, don't you know, here instead of 1, it will come 2. Correct? Now what about values of n? They are after 2, all the positive integers. That is 3, 4, 5, 6 up to infinity. For H alpha line in the Balmer series, you should take n equal to 3. Correct? Come on, for H alpha line, come on, n equals to 3. Put it here, n equal to 3. Correct? Now this wavelength of H alpha line in Balmer series is different than this wavelength. So I am just giving different symbol lambda alpha dash suppose. Come on, these are as it is, 1 upon 2 square minus 1 upon n square, but n is right now 3. For H alpha line in Balmer series, n equals to 3. So n is 3. Come on, R as it is, 2 square is 4, 3 square is 9. Correct? Now tell me, 1 upon lambda alpha dash as it is, this R as it is, come on, 9 and 4. So LCM will be 36. 9 minus 4, that is 5. So in short, it is 5R upon 36. Give it equation number 2. Now take the ratio. This upon this will be equal to this upon this. When you take this upon this, come on, denominator will become numerator. So lambda alpha dash upon lambda alpha. Now here this upon this. So let me write this first, 3R by 4. Instead of dividing, if I am writing multiplication sign, then I must invert this ratio. Now I should write 36 upon 5R. Okay, fine. And now this lambda alpha dash as it is, this is wavelength of H alpha spectral line in Balmer series, which they have given as lambda. This is the wavelength of H alpha line in the Lyman series, which they have given as lambda. This is the wavelength of H alpha line in Balmer series, which we require. Come on. Now this RR will cancel. Come on. 3, this 4 9s are 36. 9 3s are 27. 9 3s are 27 upon 5. I repeat. 4 9s are 36. 9 3s are 27 upon 5. 27 upon 5. I want lambda alpha dash, so transfer this lambda. So lambda alpha dash will be 27 lambda upon 5. Come on, 27 lambda upon 5. Got it? Fine. Kindly read the statement of number 9. Come on, have you read it? Look, in this particular question, there is a serious mistake in Gujarati medium textbook. Correct? So, you know what I have done here? There is one word given to you in the English medium textbook about Balmer series. That word is not there in Gujarati medium textbook. So, if Balmer series word is not there, and if they are talking about all 5 spectral series of atomic spectrum of hydrogen at a time, then this is the answer. I am showing you how to get this answer. But as per the statement given in English medium textbook, which is correct, this is the answer, this is the solution, this is the final answer as per the textbook. Okay? But if they do not mention about Balmer series, and then if you are supposed to consider all 5 spectral series at a time, then what is the answer? I am showing you. So that question is extra, so I just put an asterisk here. Okay, let us discuss this thing first, and later on we'll come to about the question given in the textbook. Fine. 1 upon lambda equals to r into 1 upon m square minus 1 upon n square. You must have remembered 1 upon wavelength. This whole ratio gives you wave number. Wave number. It is reciprocal of wavelength. Fine. Suppose I want 1 upon lambda maximum. Correct? So for that lambda should be taken minimum. Then only when this is minimum, the whole ratio will be maximum. So lambda should be minimum. But here the structure of formula is such that when m increases, lambda increases. Speak reverse. If m decreases, then lambda will decrease. So for minimum value of lambda, you must take minimum value of m. Correct? Minimum value of m. You must remember m values for all the 5 spectral series in atomic spectrum of hydrogen. M equal to 1, 2, 3, 4, 5. What is minimum value? 1. So m is minimum right now, which is 1. And here structure of formula is such that when n increases, lambda decreases. So for minimum value of lambda, you must take maximum value of n, that is n equal to infinity. Maximum value of n is infinity. Just put these two values in this formula. Lambda is right now minimum, so instead of lambda I am putting lambda minimum. R as it is. M is 1, n is infinity. Correct? This is 1, 1 upon infinity is 0, 1 minus 0 is 1, 1 into r, that is r. Give it equation number 1. Fine. Now the same wave number, if we want suppose minimum, so I am taking 1 upon lambda wave number as minimum. But if this ratio, if you want minimum, then this denominator should be maximized, so lambda must be maximum. Now for maximum value of lambda, you should take maximum value of m. Among all the 5 spectral series, the maximum value of m is m equal to 5. So that's why m is maximum, which is right now 5. But when you want lambda to be maximum, n value should be taken minimum. And what are the values of n? If value of m is 5, what are the values of n? 6, 7, 8, dash up to infinity. In this series, what is the minimum value of n? It is 6. That's why n equals to minimum equals to 6. Put these two values here. Come on, here. 1 upon lambda. Lambda is right now maximum. So instead of lambda, I am putting lambda maximum. And that equals to r into m is 5, n is 6. Fine. Now simplify. 1 upon lambda maximum as it is, r as it is, and 1 upon 5 square is 25, 6 square is 36. Now simplify. LCM will be 36 into 25, which is 900. 36 minus 25, it is 11 into r. 11 into r upon 900. Give it equation number 2. Now from 1 and 2, they have asked now difference of wave number. Difference of wave number. Fine. So for that we should take bigger wave number minus smaller wave number. Bigger wave number is this, because denominator is minimum. Smaller wave number is this, because denominator is maximum. Now 1 upon lambda minimum minus 1 upon lambda maximum. So it is this minus this. So it is this minus this. So it is r minus 11 r upon 900. R minus 11 r upon 900. Now 900 will be taken in LCM. 900 into r minus 11 into r, it is 889 into r. 889 as it is, value of r, Rydberg's constant 1.09737 into 10 raised to 7 meter inverse. Same value are written here, 900 as it is. Simplify, the value is 1.0839 into 10 raised to 7 meter inverse. So if you want this difference in wave number among all the 5 spectral series of hydrogen atomic spectrum, then this is the right answer. Okay? But now if you are specifically talking about only Balmer series, then that answer would be different. How much? Let us find out. Now we come to the question given in the textbook for Balmer series. Correct? This is the formula for finding wavelength. Correct? For Balmer series, m is 2. Now tell me, when n value increases, lambda decreases. When n value decreases, lambda increases. So first of all, I want this wave number to be maximum. For that, lambda should be minimum. For lambda to become minimum, n should be taken maximum. Maximum value of n is infinity. Put the value here. N is infinity. 1 upon infinity is 0. This is 2 square is 4, so it is r by 4, r by 4. And at the time lambda is minimum, so I am writing instead of lambda, lambda minimum. Give it equation number 1. Now I want same wave number to become minimum now. When this ratio is minimum, lambda should be maximum. For maximum value of lambda, you should take minimum value of n. Once you say that minimum value of n, then what are the values of n? For Balmer series, values of n are 3, 4, 5, 6, dash, dash, dash up to infinity. In this series, what is the minimum value? 3. So n value should be taken minimum equal to 3. N equals to minimum equal to 3. Put it here. 1 upon lambda. Lambda is right now maximum, so instead of lambda I am putting lambda maximum. R as it is. 1 upon 2 square minus 1 upon n square, but n is right now, come on, n is 3, correct? N is 3. N is 3, so 3 square. Now simplify. R as it is, 1 upon 2 square is 4, minus 1 upon 3 square is 9. LCM will be 9 into 4, that is 36. 9 minus 4, that is 5 into r upon 36. 5 into r upon 36, give it equation number 2. Now from 1 and 2, come on, we are asked to find out difference in wave number. Again I am telling you, bigger wave number minus smaller wave number. This is bigger wave number because lambda is minimum here in the denominator. Here this wave number is less because denominator is more, correct? Bigger minus smaller wave number will give you difference in wave numbers. 1 upon lambda minimum minus 1 upon lambda maximum. In short, it is this minus this. So it is this minus this. So it is r by 4 minus 5 r by 36. R by 4 minus 5 r by 36. LCM will be 36. Come on, 4 9s are 36. So 9 will be multiplied here. 9r minus 5r, that is 4r upon 36. Come on, don't you know 4 9s are 36. So it is r by 9. Correct? Value of Rydberg's constant is known to you, 1.09737 into 10 raised to 7 meter inverse divided by 9. Now this answer is 1.219 into 10 raised to 6, that many meter inverse. So if it is only Balmer series, this is the right answer. If you are talking about all 5 spectral series of atomic spectrum of hydrogen at a time, then this is the answer. Got it? Nowhere you will find this explanation. I have done it here just for your good knowledge and satisfaction. Okay? Fine. Now kindly read the statement of number 10. Come on, have you read it? Look, energy of electron is in the ground state for electron in hydrogen atom. For ground state, what is energy? Minus 13.6 electron volt. Correct? Now, its energy becomes minus 3.4 electron volt because it goes in which state? They have given in number 10, you see the statement. In number 10, correct, they are talking about first minimum excitation potential. First minimum excitation potential. So you have to excite the electron from ground state. But because you want to supply minimum excitation energy, then you should just transfer it into very next excited state. Very next state. When you go higher in the energy level diagram, when you go higher, the states are excited. So when electron is already lying in n equal to 1 orbit, and from there after supplying minimum energy you want to excite it, then you have to send it into the next state. Next state is n equal to 2. In n equal to 2, what is the energy of electron in hydrogen atom? Minus 3.4 electron volt. Correct? What is the initial energy? Minus 13.6. Later it becomes minus 3.4. Then how much is the energy which you require to supply? Let us find out. Because you are increasing the energy of electron, let us find out increase in energy of electron. Increase means final minus initial. So it is E2 minus E1. So it is this minus this. This minus this, minus minus plus. So minus 3.4 plus 13.6. 13.6 minus 3.4, answer is 10.2 electron volt. This is the minimum excitation energy because unit is electron volt, correct? But we are not asked to find out minimum excitation energy. We are asked to find out minimum excitation potential. It is also called first excitation potential. First excitation potential is simply you just transfer this E in the denominator, okay? Or you remember, as many electron volt, that many volt. As many electron volt excitation energy, that many volt excitation potential. I repeat, as many electron volt excitation energy, that many volt excitation potential. So excitation potential will be 10.2 and write the unit only volt because potential has unit volt. What is the formula for finding excitation potential? It is excitation energy divided by charge of electron, magnitude of charge of electron, correct? When you divide on both the sides by E, here answer is 10.2 volt, 10.2 volt, got it? I repeat, this is minimum excitation energy, this is minimum excitation potential, okay, fine. Now kindly read this statement of number 11. Read it? Look. Energy of electron in the ground state in the hydrogen atom is minus 13.6 electron volt. What are you supplying? You are supplying 12.09 electron volt of energy. So its total energy will become now this plus this, answer is minus 1.51 electron volt. Wait. Now energy of electron in electron volt for electron in hydrogen atom, you know by formula minus 13.6 upon n square, that many electron volt. This is also energy of electron only, in hydrogen atom only, in electron volt only. So we can match this value with a standard formula minus 13.6 upon n square. Just equate this value with this value. Minus minus will become plus, n square you may transfer here, 1.51 will come down. 13.6 upon 1.51, that answer is 9. So n square value is 9. Take square root on both the sides, then you will get n equal to 3, right? So when you supply this much energy, and total energy of electron will be this much, and when total energy is this much, corresponding state is n equal to 3, or you can say third state, or you can say second excited state, fine. Kindly read the statement of number 12. Read it? Let us find out decrease in angular momentum of electron as it makes a transition from third orbit to second orbit. Decrease in angular momentum means initial angular momentum minus final angular momentum. Initial angular momentum is nh upon 2 pi, because n equal to 3, I am writing here 3, minus final angular momentum is, come on, again nh upon 2 pi, but final orbit is n equal to 2, that is why I am putting n equal to 2. 3h upon 2 pi minus 2h upon 2 pi will give you h upon 2 pi. Simple. This is decrease in angular momentum. What is the corresponding average torque which we have to find out? Average torque is change in angular momentum divided by time. Change in angular momentum is this much, h upon 2 pi divided by corresponding time interval. Value of H, everybody knows, Planck's constant 6.625 into 10 raised to minus 34 joule into second upon 2 into pi is 3.14. What about delta T? Time interval you are given in the statement 1.2 into 10 raised to minus 8. Come on, that many second. Simplify, answer is 8.79 into 10 raised to minus 27. Because you are finding torque, unit is Newton into meter. Correct? Kindly read the statement of number 13. Read it. What is the formula of R? That is radius of nth circular orbit of an electron. R equals to epsilon 0 n square s square upon pi m z is square. What is relation of R with Z? It is inverse proportionality relation. Correct? So, for that element among given 4 options for which Z is maximum, naturally this radius of orbit would be minimum. Among all the 4 options in the textbook, this is the element magnesium for which atomic number is 12, which is maximum among given elements. Because this is maximum, naturally this radius will be minimum. So, when Z is maximum, R will be minimum. Simple. Kindly read the statement of number 14. Read it? Come on. For elements like hydrogen, there are 2 more elements given to you in the statement A and B. What have they given else? That excitation potential, ionization potential for element B is greater than ionization potential of element A. If VB is greater than VA, just pick reverse, VA less than VB. Correct? When ionization potential is less for element A, corresponding ionization energy also will be less for element A. So, when VA is less than VB, come on, EA is less than EB. Mind well, this is not the total energy, this is ionization energy, which is the minimum energy which we have to supply in order to convert neutral atom into ion. Correct? Fine. Now, if ionization energy is less for element A, it means to say you have to supply less amount of energy to remove 1 electron from atom of element A. Correct? But why do you require less amount of energy to supply? It means to say that that electron in atom of element A must be far from the nucleus. Correct? Having very weak binding with the nucleus. That's why you require to supply less energy in order to make it freed. Correct? So, when that electron in the atom of element A is far from the nucleus, its orbital radius must be more. That's why I am writing Ra greater than Rb. Got it? Orbital radius of electron in atom of element A must be greater than orbital radius of electron in atom of element B. Simple. Kindly read the statement of number 15. Read it? Remembered Moseley's law. Moseley's law for finding frequency of K alpha radiation was under root F, was equal to Cz minus C. If you know the frequency of K alpha radiation, ultimately using Moseley's law, what you can find out? Z, and Z is the atomic number. So atomic number is the characteristic of given element is given by frequency of K alpha radiation. Frequency of K alpha radiation is the characteristic of a given element used as an anode in the X-ray tube. For different elements used as anode in X-ray tube, the frequency of K alpha radiation is different, correct? For a given element it is fixed. So that frequency would determine the atomic number and thereby type of element. Got it? Read the statement of number 16 now. Come on, read it. Tell me, whatever the accelerating voltage may be in X-ray tube, but ultimately what is going to be emitted? X-rays. X-rays are none but electromagnetic waves, and for all electromagnetic waves in vacuum they have same speed, and that same speed is shown by symbol small c. What is the value? 3 into 10 raised to 8 meter per second. This speed is irrespective of value of accelerating voltage, correct? Read now statement of number 17. Come on, read it. Recall Moseley's law. Moseley's law is under root f equals to Cz minus C. For first element, I am writing here F1. Here I am writing Z1. Atomic number for first element they are given 43. So this is 43. 43 into C minus C, that will give you 42 into C. Okay. For second element, here you should write F2. Correct? Here you should write Z2, that Z2 is given to you as 29. 29 into C minus C. 29 into C minus C, that is 28 into C. Correct? Fine. And now, take the ratio. This upon this will be equal to this upon this. Under root of F1 upon F2, that equals to this upon this. C will cancel. 42 upon 28. 42 upon 28. 14 3s are, 14 2s are. So it is 3 by 2 now. Correct? Don't you know C equals to F lambda equals to constant? When F into lambda is constant, you may write F1 lambda 1 equals to F2 lambda 2. Find out F1 upon F2 from here. F1 upon F2 would be lambda 2 upon lambda 1. This F1 upon F2 can be replaced by lambda 2 upon lambda 1. So under root of lambda 2 upon lambda 1. And right hand side as it is. Okay. Take squares on both the sides. When you take square, square root will vanish, giving you lambda 2 upon lambda 1. 3 square is 9, 2 square is 4. This is the first value of wavelength, which in the statement you are given as lambda. Second value we are looking for 9 by 4 as it is. Find out lambda 2, it will be 9 lambda upon 4. 9 lambda upon 4. Fine. Kindly read the statement of number 18. Come on, have you read it? Look, this is energy level n equal to 1. This is energy level n equal to 2. This is energy level n equal to 3. Fine. K alpha radiation is emitted during transition of electron from n equal to 2 to n equal to 1, and corresponding frequency they are given as F1. So, energy of one X-ray photon having frequency F1, you know it is E1 equals to HF1. For emission of K beta radiation, the responsible transition of electron is from n equal to 3 to n equal to 1. At that time, the frequency is given to us in the statement as F2. Then corresponding X-ray photon energy would be E2 equals to HF2. Come on. For the emission of L alpha radiation, the responsible transition of electron is from n equal to 3 to n equal to 2, and corresponding frequency they are given in the statement as F3, and its X-ray photon will have energy E3 equals to HF3. Now from the figure we can make out that summation of these two energies E1 plus E3 should be equal to this energy, that is E2. So E1 plus E3 must be equal to E2. Here energy is E1, here energy is E3, and this energy is E2. So E1 plus E3 must be equal to E2. E1 plus E3 must be equal to E2. Place the values. E1 is HF1, E2 is HF2, E3 is HF3. Come on, HF1 plus HF3 is equal to HF2. H will be getting cancelled throughout the equation. You will get the answer F1 plus F3 equals to F2. This is the right answer. You may not find this answer in the textbook, but this is the right answer. F1 plus F3 equals to F2. Okay. In Gujarati medium, they have committed a mistake. I don't know about English medium. You may check it, but this is the right answer. Okay. Fine. Now kindly read the statement of number 19. Have you read it? Look, we have one electron in the ground state in the atomic spectrum of hydrogen. In the atom of hydrogen, we have one electron in the ground state having energy how much? Minus 13.6 electron volt. And to that electron, how much energy you are supplying? You are supplying energy 12.1 electron volt. So minus 13.6 plus 12.1 will give you minus 1.5 electron volt. Fine. Minus 1.5 electron volt is the energy of electron in the third state. So that's why here shown the third energy level. Come on. So in short, you have sent electron from here to here. Correct? Now, after some time, it so happens that it makes transition back towards the ground state. But it can have two options, two choices. It may first of all make transition from n equal to 3 to n equal to 2. Then after it may make transition from n equal to 2 to n equal to 1. Correct? Stage wise. Okay. It may make two transitions to come to the ground state. Or it may transit directly from this third state to n equal to 1, that is ground state. So what is the answer? The possible transitions are maybe number of transition only 1, or maybe number of transition 1 and 1, that is 2. So final answer is number of transitions may be 1 or 2. Minimum 1 and maximum 2. Minimum 1, maximum 2. Got it? Fine. Come on my dears, let us begin with the numericals from exercise. Kindly read the statement of first numerical. Come on, have you read it? Listen. If you remembered in one of the illustrations in textbook, we had talked about Bohr's correspondence principle, and in the same numerical we had obtained expression of frequency of revolution of electron in nth orbit and that n value was very large, and at that time that frequency of revolution was this much, f equals to 2rc upon n cube. If value of n is very large, then this becomes also the frequency of radiation emitted during transition of electron from n plus 1 to nth orbit, if n value is very large. If n value is not very large, then also this expression gives you frequency of revolution of electron when orbiting around the nucleus. Okay? Please kindly remember this small formula, many times it will be useful to you. F equals to 2rc upon n cube, where r is Rydberg constant, small c is velocity of light in vacuum, n is given principal quantum number or order of orbit. Fine. Now these two as it is, Rydberg constant is 1.09737 into 10 raised to 7 meter inverse, c is velocity of light in vacuum 3 into 10 raised to 8 meter per second, and this value of n, as long as electron remains in n equal to 2 orbit, in that much time interval, how many revolutions are completed by that electron, that is what we are looking for. So we should take n equal to 2, correct, in second orbit. N equals to 2, simplify, answer is 8.23 into 10 raised to 14. These many revolutions per second means second inverse. So I am writing here time in second, opposite I am writing number of revolutions. These many revolutions are finished in 1 second. So in 1 second, these many revolutions are getting finished. In 1 second, if this many revolutions are getting finished, then electron remains in n equal to 2 orbit for how much time? In the time equal to average lifetime. Average lifetime they have given in the statement as 10 raised to minus 8 second. In 1 second, if these many revolutions are completed, then in 10 raised to minus 8 second, how many revolutions will get completed? Come on. This into this upon this. Answer is 8.23 into 10 raised to 14 into 10 raised to minus 8. Come on, 14 minus 8, that is 10 raised to plus 6. So answer is 8.23 into 10 raised to 6. These many revolutions will get finished in the given time interval, which is 10 raised to minus 8 second. Got it? Fine. Kindly read the statement of second numerical. Read it? Look, we are given transition of electron from third excited state to ground state. Third excited state means fourth state, and into the ground state means in n equal to 1. Okay? So transition is from n equal to 4 to n equal to 1. When electron makes transition from higher ith order orbit to lower kth order orbit, at that time the wavelength of radiation emitted is given by this formula, 1 upon lambda equals to r into 1 upon nk square minus 1 upon ni square. This r as it is, nk is the lower order of orbit, which is right now 1, ni is higher order of orbit, which is right now 4. Simplify, this r as it is, 1 upon 1, that is 1, minus 1 upon 4 square is 16. So now it is 16 minus 1, that is 15 upon 16 into r. Come on, take the reciprocal. So lambda will be 16 upon 15 into r. 16 upon 15 into r. 16 as it is, 15 as it is, Rydberg constant 1.09737 into 10 raised to 7 meter inverse. Simplify, answer is 9.72 into 10 raised to minus 8 meter. Perhaps in the textbook you may find 9.92. It is wrong. Correct answer is this, 9.72 into 10 raised to minus 8 meter. Okay. They also asked the corresponding energy of one photon. Energy of one photon is given by this formula, E equals to hf, where f is c upon lambda. Values of h and c are known to you. What is h? Planck's constant. What is c? Velocity of light in vacuum. Come on, Planck's constant 6.625 into 10 minus 34 joule into second. C is velocity of light in vacuum 3 into 10 raised to 8 meter per second divided by lambda. Come on, lambda value is 9.72 into 10 raised to minus 8. Same value are written here, but normally it is a tradition to find out such photon of such energy of photon in electron volt. So we are going from joule to electron volt. When you want to convert value of energy from joule to electron volt, you should divide by 1.6 into 10 raised to minus 19. Got it? And now this answer comes out with 12.76, this many electron volt. Got it? Kindly read the statement of number 3. Read it? Come on. For Balmer series, 1 upon lambda equals to r into 1 upon 2 square minus 1 upon n square. What are the values of n? After 2, all the positive integers, that is 3, 4, 5, 6, dash, 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 up to infinity. Here we are asked to find out the maximum wavelength. If you want lambda to be maximum, then n value should be chosen minimum. N equals to minimum. What is the minimum value in this series? It is 3. So n equals to 3. Put it here. When n is 3, it is 3 square. Come on. 1 upon 2 square are written here. Minus 1 upon n is 3. So 3 square. But at that time, when n is minimum, lambda is maximum. So instead of lambda, I must write lambda maximum. Fine. Simplify. R as it is, 1 upon 2 square is 1 upon 4. Minus 1 upon 3 square is 9. Now simplify. 9 into 4, that is 36, will be taken in LCM. Now 9 minus 4, that is 5 into r upon 36. Now take reciprocal on both the sides. So when you take reciprocal here, you get lambda maximum. When you take reciprocal here, it is 36 upon 5r. 36 as it is, 5 as it is. What about Rydberg's constant? 1.09737 into 10 raised to 7 meter inverse. And then you will get the value of lambda first in meter, because value of r you are putting in meter inverse. Come on, lambda maximum in meter comes out to be 6563 into 10 raised to minus 10. That many meter. But 10 raised to minus 10 meter is nothing but 1 angstrom. So it is 6563. These many angstrom. We are also asked to find out corresponding wave number. Wave number is nothing but reciprocal of wavelength. Right now wavelength is lambda maximum. Its reciprocal would be 1 upon lambda maximum. 1 upon, suppose this lambda maximum I am putting in meter. That meter value is this. Come on, 6563 into 10 raised to minus 10. 6563 into 10 raised to minus 10. This answer comes out to be 1.52 into 10 raised to 6, because this value you are taking in meter, going up will become meter inverse. Meter inverse. Okay. Kindly read this statement of number 4. Come on, read it. For Balmer series of hydrogen atomic spectrum, 1 upon lambda equals to r into 1 upon 2 square minus 1 upon n square. What are the values of n? After 2, all the positive integers, that is 3, 4, 5, 6 up to infinity. But now they are talking about H alpha line in the Balmer series. For H alpha line, we should take first value of n in this series, that is 3. N equals to 3. Come on, 2 square is 4. Because n is 3 right now, 3 square is 9. Now, simplify. This is 9 minus 4, that is 5r upon 36. Give it equation number 1. And this is the wavelength of H alpha line of Balmer series. Let it be shown by symbol lambda alpha. Now we are talking about Lyman series. For Lyman series, this formula would appear this way. Instead of 2, you should write 1. That's all. Instead of 2, you should write 1. Fine. Now what are the values of n? After 1, all the positive integers, that is 2, 3, 4, 5, dash, 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 up to infinity. But again they are talking about H alpha line only for now Lyman series. Then you should take first value. For H alpha line, you should take first value in this series, which is 2 right now. N equals to 2. Put it here. 1 upon 1 is 1. When n is 2, 2 square will be 4, minus 1 upon 4. Minus 1 upon 4. Come on. At that time, whatever wavelength you will get, it will be wavelength of H alpha line of Lyman series, which is different than this wavelength. That's why I am putting different symbol, lambda alpha dash. Now R as it is. Now 1 minus 1 by 4, it is 3 by 4. Give it equation number 2. Now take the ratio. Come on. This upon this will be, come on, this upon this will be this upon this. Come on, this upon this, when you take denominator will become numerator. So lambda alpha dash upon lambda alpha. And when you take this upon this, come on, this I am writing as it is 5r upon 36. Instead of division, I am just showing sign of multiplication. So this ratio should be inverted. 4 upon 3r. R1s are getting cancelled. 5 4s are 20. 36 3s are 108. And now this lambda alpha is what? Wavelength of H alpha radiation, wavelength of H alpha spectral line in case of Balmer series. In case of Balmer series, wavelength of H alpha line, they have given in the statement 6563 angstrom. If you are putting this value in angstrom, naturally this also will be obtained in angstrom. So this lambda alpha, they have given 6563 angstrom. This right hand side 20 upon 108 as it is. Find out lambda alpha dash. Answer is 1215, that many angstrom. You must put this empty circle exactly at the center. Okay. Don't put it on the right hand side. This is the correct symbol for showing angstrom. Okay.